Thank you. It's my pleasure to present the joint work with my PhD advisor, Matthias, and our collaborator in Vienna, University of Technology, Anela, Lolic. This is about quantified first-order S5 and interpolation. So let me start a few words about interpolation, why it matters, and what is the role in. Well, first of all, my talk is not technical. It's focused on the idea, and the rest of the technical things like proofs you can see in the paper. So, quick interpolation. It's stated as logic has interpolation. It's imply B is valid in the logic, and then there exists formula E interpolation such that imply is valid in the logic and imply B is valid in the logic, and E uses only common language between L and B. So why it is important? The reason for the interpolation is that it acts like a bridge between the premises and conclusion. So you cannot have arbitrary conclusions in the language if it doesn't share common language with the premises, with assumptions. So it restricts inferences in the sense that interpolation guarantees that local contradictions stay on the local side, and it doesn't affect the whole system. Philosophically, it resonates with the principle of relevance. So argument should not rely on symbols or concepts that are not common, that are alien to both premises and conclusion. So only what is shared with the goal matters for driving the goal. Now, maybe most favorite part for you, application in the computer science and Turing provers. So in database reasoning, it has like local error stays locally. For example, queries only if we share vocabulary. In verification reasoning, components communicate via their interfaces. Resolution is set of supports. Here is also it's connected with a set of support properties, and keeping inconsistencies local is the main point for the interpolation. So a few words about algebraic view. It connects syntactic logic to algebraic structure. In propositional logic, it is corresponding to the lattice theoretic factorizations via joins and loops through the shear subalgebra. By the well-known results of Maximova in propositional logic, it's already given classification which logic have interpolation. And well, in first-order logic, algebraization fails because it's impossible to determine which first-order logic have interpolation. Okay, so interpolation is also well connected with best definability theorem, which is very important, which connects syntactic and semantic settings for the logic. It shows that implicit and explicit definable are equivalent. In first-order logic, it holds, but outside of the first-order logic, for example, in modern logics, in first-order S5, it doesn't hold. So motivation for our research is that interpolation holds in first-order logic, but it doesn't hold in outside of the first-order logic. For example, first-order model S5. So it was already defined by Kitfine that shows that first-order S5 doesn't interpolate, although propositional S5 has interpolation. It's decidable. So it was shown in this third part that what Kitfine did. He expanded theory T with these two axioms and showed that P is implicitly definable in this theory, but not explicitly definable. So what we do, let me first say a little bit about quantified S5. So the language I denote here is the QML, and we restrict our language with no functions and no individual constants. Also, it is easy to see that functions can be moderated with via predicate symbols. Quick model is tuple of words, relation, domain, and variables, where the relation is equivalence relation, and we focus on constant domain D, because the tool we are using works only for constant domain. So all words are in equivalence class, mutually accessible. A formula true in one word is true in all words in the class. So the box and diamond are corresponding to universal existential quantifiers over words. We have rigid variables, so each variable designates the same object across all possible words. However, predicate interpretations may vary from word to word, so they are word dependent. And this last formula, equivalences, are valid in S5. So this is very important because we are using, our argument is based on this fact that S5 has equivalence classes. For example, in the first picture, if you take in the word box P false at any word in the C1, this is because P is false in the word P, and they are all equivalent. It's equivalence class, so they are all connected with each other. So the idea is that the counter model needs only one equivalence class. If P is false in some word of the class, then box P will false everywhere in the class. And so we only need one word in the class. So the idea is, although quantified S5 is doesn't have interpolation, can we recover some fragments which have interpolation? Well, it doesn't have interpolation because there's no analytic calculus. But what we do is we embed S5 into a richer two-sorted first-order logic, I denote it as SL, where we have two sorts of variables for words and for objects. And there is a term separation, so the terms are separated, and we don't use any function symbol, so it's not to have any other variables for word class. And another thing is that when we translate quantified S5, you get one variable class for word domain, so for word quantifiers. So this SL has nice analytic calculi. It has nice theoretic properties. It admits cut-elimination, from which follows the mid-second theorem, and from which follows Meyer lemma, and so we get interpolation. So here it is how actually what formulas of model logic, model S5 correspond to formulas in SL. What we do, we have only predicate symbols. So predicates, NR predicates are extended by one position for word position, and the word is in front. And the formulas have arbitrary object quantifiers, but only one variable class of word quantifiers. So we only have one word variable. And validity is preserved by the translation under the obvious correspondence between the models. So here is a standard translation how formulas from model S5 are translated to SL. Key fact is that all words are connected, as I mentioned, and we work with constant domains. So it consequently doesn't matter from which word variable we start. If every subformula is in the scope of some model operator. So this is a simple example of the translation of model formula in two-sorted language. Here you see that box and diamond becomes quantifiers over words. So one key point here is that in translations of model formulas, each formula is always bound by the innermost word quantifier in the scope. And so formula system is in a cell in which word quantifiers cross-bind express relations which are not expressible in the SL. So actually, from the formula, the translated formula in the two-sorted Versoden logic, we can actually see that the formula originally comes from model S5. So we define one word variable fragment of a cell, and we have that let's say that SL for V for one variable fragment of a cell contains formulas, or in the two-sorted logic SL, which in which every subformula is only bound by the innermost word quantifier. And the only free variable that appears is the word variable. For any quantified model S5 formula, its translation belongs to this one variable fragment of a cell and can be expressed with a single bound word variable. And we have also retranslation. Another formula F is valid in constant domain S5, but it is valid in the two-sorted SL. Now let's see the nice theoretic properties of this first-order two-sorted first-order SL. So it has cut elimination, and the proof is simple. You just consider rules in the usual first-order ones. You just make sure that the sorts are not mixed, and from which follows that it has extended. We call it extended mid-sequent theorem. So for a cut-free SL proof of a sequence with Frenet's word quantifiers, there is a mid-sequent for which above it only word quantifier rules and propositional rules occur, and below only object quantifiers and structural rules occur. So it is a simple sketch. It is nothing, just simply you follow permutation of the source variables. Then the next property is the Meyer-Stein lemma for this SL. And given a cut-free derivation of sequence, fixed partition, and construct the interpolant in such a way that it satisfies these two conditions. So non-logical symbols of E lie in the intersection of those both sides, and you respect so it's well sorted. So the separation of sorts is the key idea here. So what we get from Meyer lemma great interpolation theorem for SL. So we get for Krenek's fragments for object quantifiers and dually for the word quantifiers. But it's not nice because everything is not smooth as it seems because it might not every interpolant in SL corresponds to the interpolant in the original model language. Yes. So, for example, this formula, which is a standard quantifier sheet in constant domain, here it is valid because we assume that we have constant domain S5, but here the translation doesn't work, doesn't hold. So now we have, which fragments actually have retranslation? So here, let's start with any interpolant obtained with in SL for Pitt Fine's counterexample is not equivalent to any formula in two-sorted first-order logic in the syntax of quantified S5. So general strategy we use is we take this two-sorted setting. We have this separation of sorts. We find interpolation there, and then we ask, can we translate it back? So if the translation is possible, then we are done. Yes, so we have three cases so far, three fragments we covered, which do have interpolation, so which have corresponding retranslations in original S5. So the first proposition S5, it is known already by Pitfine, but here we show it with Meyer lemma. And so actually translation, well, each model proposition formula becomes a monadic first order formula over the world sorts, and the interpolant is also monadic. Yeah, this is a strategy. The second case is big model fragments. So we have arbitrary object quantifiers and we have arbitrary model world quantifiers, but they are big. So, for example, weak forks offers only negative, and weak diamond only offers only positive. And under these restrictions, the two-sorted interpolant is can be held in the one variable fragment, and therefore we can retranslate back to S5. Yeah, if both quantifiers, object and world quantifiers are weak, then we have a propositional interpolant. And the third case is the Prenix fragment. So object quantifiers are Prenix, and we can assume the dual is also working in this easy consequence. We have arbitrary model quantifiers, and fit sequence is purely propositional because we get only world sorts. Yeah. So Prenix fragment have other nice consequences, which I present as a corollary. It has Herborn disjunction for every valid Prenix formula in S5. We had it may contain arbitrary modalities in the matrix. Then there is a Herborn disjunction equivalent in Herborn disjunction in two-sorted first logic, which is equivalent to the original formula given in this form. And another corollary is solemnization. Existential object quantifiers can be solemnized with terms that do not need to depend on the world variables. Another corollary is that it has second epsilon theorem. Every epsilon proof of the quantifier fit consequence in the Prenix fragment reduces to Herborn disjunction only objects. And so the second epsilon theorem holds for Prenix as well. Yeah, well, the simple idea here is just we reorganize the proof with respect to object quantifier rules, and we don't touch the model quantifiers. So to sum up, what we have done, we have embedded S5 into richer two-sorted logic. We have separated world and object terms. We have omitted function symbols. And what we do, we have two-sorted separation, we have path elimination, mid-sequence theorem, Meyer lemma, and we obtain interpolation. And then we try to retranslate back. Yeah, so what can be extension, like what we have asked to work on is, well, actually to compare interpolants in SL and in original model S5, whether they are smaller than the original one, but we didn't have done it yet. Yeah, so this is.
Thank you.